welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video, I'm going to explain Carlo Rovelli's response to the mystery of Einstein's entanglement via his relational quantum mechanics. As you will see, it provides no answer at all. To keep this video short, I will omit many details. You can find those missing details in our book, Einstein's Entanglement, published with Oxford University Press in 2024, and our published papers linked in the video description. Here is Rovelli's interpretation of quantum mechanics called Relational Quantum Mechanics. The quantum state provides information pertaining to the quantum system and whatever it interacts with, given their interaction history. Here's what Rovelli says about Schrödinger's cat in Is Quantum Reality in the Eye of the Beholder on World Science Festival YouTube channel. I'll put a link in the video description. The cat is either alive or dead with respect to himself because he's in a definite state. But for me, looking at the box, the cat is neither dead nor alive because with respect to me, neither of these two are realized. We never see cats that are half alive and half dead because quantum theory predicts that we never see these sorts of things. It predicts that we will see cats either alive or dead, but that's wrong. As I explained in this video on Schrödinger's cat, any pure state, such as 50% live and 50% dead here, is the outcome of some measurement. If Schrödinger's cat is in a quantum superposition of two possible outcomes, it is a quantum binary digit, or qubit for short. For example, to make the double slit qubit, we simply reduce the intensity of the laser illuminating a pair of slits until it is only emitting a few photons at a time. This is the two-dimensional Hilbert space showing the basis vectors, measurement outcomes, for two measurements on the double slit qubit. Don't worry about the fancy language. Everything will make sense. Slit 1 and slit 2 are the pure state outcomes of a Witch slit measurement. Since our qubit is in the state psi equals slit 1 plus slit 2 over root 2, the outcomes of a Witch slit measurement will be slit 1 with 50% probability and slit 2 with 50% probability. Slit 1 plus slit 2 over root 2 and slit 1 minus slit 2 over root 2 are the pure state outcomes of an interference measurement. Notice that our state psi is an outcome of the interference measurement. Thus, if we do an interference measurement of our qubit in the state psi shown, the result will be psi itself with 100% probability. Now let's see what all of this means physically. When we place the detector immediately behind the slits, literally like right up against them, 50% of the photons land in the image region of slit 1. Psi becomes the slit 1 state. The other 50% of the photons land in the image region of slit 2. Psi becomes the slit 2 state. This is a Witch slit measurement, and slit 1 and slit 2 are its pure state outcomes. When we place the detector far from the slits compared to the slit separation, all of the photons land in the image regions of constructive interference bands of the classical double slit experiment. This is an interference measurement complementary to the Witch slit measurement. That means psi doesn't change, so this measurement outcome literally represents 50% slit 1 plus 50% slit 2. Physically speaking, this just means that the intensity of the light from slit 1 is equal to the intensity of the light from slit 2 everywhere along the detector in the classical counterpart, since the detector is very far away from the slits. It's not really mysterious. Now here is the Hilbert space showing the measurement outcomes, pure states, of two complementary measurements, where the state of the Schrödinger's cat qubit is an outcome of one of the measurements. Just like the pure states, slit 1 and slit 2 are the possible outcomes for the Witch slit measurement on the double slit qubit, the pure states live and dead are the possible outcomes for the open the box measurement on the Schrödinger's cat qubit. If you do that measurement on this state, half the time you will find the cat is alive and half the time you will find the cat dead. But if Schrödinger's cat really is in a quantum superposition of 50% live plus 50% dead, that is, if it really is a qubit, then you can rather choose to do the complementary measurement on that state, whose outcome would be the state itself, 50% live plus 50% dead. Just like when you do the interference measurement on the double slit qubit, you get literally 50% slit 1 plus 50% slit 2. Every outcome is that. It's just the interference pattern. It's nothing special, right? You're going to have to come up with something like that here. If it's a qubit, that has to be possible for this. That's what quantum mechanics predicts. And further, why would the cat be either alive or dead? Those are states for the open the box measurement. But what if the person outside decides to do some other measurement? Then the cat will have to be in one of the outcome states for that measurement, not alive or dead. So if the cat is really in a definite state, then it must be in a definite state for the measurement the person outside decides to make, if there's going to be self-consistency, right? So relational quantum mechanics does nothing to solve the mystery of qubit superposition. What about quantum entanglement? Does relational quantum mechanics do anything to solve the greatest mystery in physics? Brian asks, how does relational quantum mechanics illuminate, say, entanglement? You measure two distant particles, and if one is up, the other is always down. And we say, how does that happen? And of course, we don't really have a story to tell. That's really convincing in the usual approach. Do you have a story to tell in this relational approach that sheds more light on it? Rovelli answers, yes, it is a story which doesn't take away the strangeness of the phenomena. The phenomena strange, and it remains strange. Imagine that you measure something here and you measure something there. You're cheating, because who is seeing here and there at the same time? Nobody. Well, Carlo, dude, if I'm in the lab and I have all my equipment out on the optics bench, yes, I'm standing there seeing the whole thing at once. But let's move on to this ridiculous claim. To compare that they have seen the same thing, you have to wait until they communicate with one another. And once they communicate to one another the information, then you can make the comparison. He's talking about Alice and Bob, making the measurements on the different wings of this experiment, right, with the two entangled particles, and then later communicating with each other. Oh, what did I see in trial 1, and what did you get on trial 1, etc. Now let's see what is the world with respect to the final observer that gets the information. In other words, once they get together and they compare the information. But again, like I said, dude, it's on an optics bench. Yeah, I'm standing right there. Even the original experiment had these giant wings there. John Clauser was standing right there next to both of them at the same time. Ridiculous. There's no non-locality anymore because all the information is sent locally. Brian asks, but when I unravel that story, wouldn't I still need to explain why there's this correlation that whenever this one's up, that one's down, and whenever this one's down, that one's up? When each is 50-50 up, down, how do they always anti-correlate in this way without communicating with each other? Brian's not falling for that ridiculous story, is he? And Carlo starts to answer, and Brian says, oh, wait a minute. Are you going to say that I'm assigning the probabilities to the particles still? It's not the particles. It's the outcome of the thing. Am I thinking there's really an outcome here at the same time there's an outcome over there that anti-correlate? What? No shit there is. Carlo answers, exactly. I think that the mistake is to always assign absolute properties to particles instead of relative to something else. Okay. But where is objective reality? Physics doesn't stop with a fragmented collage of disparate, individual, subjective space-time models of reality. The point of physics is to reconcile those individual, subjective space-time models with each other into one objective space-time model of reality. Right. Ironically, Carlo gave this advice in his 1996 paper, where he also introduced the relational quantum mechanics. You can see in this quote that he suggested we reconstruct quantum mechanics like Einstein reconstructed the Lorentz transformations leading to their physical meeting. This is ironic because the quantum reconstruction program shows us that quantum mechanics is based on the relativity principle. The laws of physics are the same in all inertial reference frames. Here, for example, is how Randy Knight could mirror his introduction to special relativity for an introduction to quantum mechanics. You can see right there, right? You have the relativity principle, and all the results of quantum mechanics follow from this one simple statement, just like he said the same thing there for special relativity, right? And as I've explained in several videos, some shown here, that means the reason we have qubit superposition and entanglement is because of the equality of all perspectives. So, the quantum reconstruction program, recommended by Rovelli in the paper where he introduced relational quantum mechanics, does not force us into the undesirable omission or violation of intersubjective agreement on the model. In fact, the quantum reconstruction program reveals The key to explaining our past and predicting our future subjective experiences is the equality of the perspectives of the experiencers when constructing an intersubjectively agreed upon and comprehensive objective model of reality. In other words, reality is not a fragmented collage of different subjective experiences from different perspectives. It's a comprehensive and coherent integration of those different subjective experiences per the equality of all perspectives relative to all perceptual origins, animate or inanimate. If you want to know more of the details, you can watch the videos I referenced earlier or read our book, Einstein's Entanglement, Bell Inequalities, Relativity, and the Qubit.